Hello everyone. Tonight, we're going to sink into one of the most fascinating and mysterious objects in the universe, the neutron star. These are not just any stars, these are cosmic fossils, time-compressed, matter-bending, gravity-heavy echoes of something that once roared with nuclear fire. But now, they whisper, they spin, they pulse. And inside lies a puzzle so dense, so extreme, that even our best physics struggles to describe it. Please let me know where are you listening from and what time it is for you. It's always a beautiful reminder of how vast and connected we are under the same sky. Let's begin at the edge of a dying star, where the story of a neutron star begins. The death of a giant. A neutron star isn't born like most stars. It's not forged in calm, it's born in chaos. It begins as a massive star, maybe 10 to 25 times more massive than our Sun. These behemoths live fast and burn bright, fusing hydrogen into helium, then helium into carbon, and onward up the chain until their core becomes iron. Iron is the end of the stellar road. It doesn't release energy when fused, it absorbs it. So when the star's core fills with iron, it's like pulling the plug on a cosmic engine. Gravity, once balanced by the fire of fusion, now wins. The star collapses in on itself. Its outer layers rebound violently off the core in an unimaginably powerful explosion, a supernova. For a brief moment, that star outshines an entire galaxy. But what's left behind is the real mystery. From collapse to core. The core, too massive to become a white dwarf, but not quite heavy enough to become a black hole, implodes. Electrons and protons are squeezed together, merging into neutrons. Billions upon billions of them. The result is a single, solid, atomic nucleus the size of a city. A neutron star. It's only about 20 kilometers wide, just 12 miles across. But it contains more mass than our entire Sun. Imagine a teaspoon of this matter. It would weigh over 1 billion tons. Heavier than Mount Everest in the palm of your hand. That density is hard to wrap our minds around. Atoms, the building blocks of matter, are mostly empty space. In a neutron star, that space is gone. The very concept of solid takes on a new meaning here. It's no longer just matter, it's matter under pressure, unimaginable on Earth. The surface, not what you expect. The outermost layer of a neutron star is often called the crust. But don't think of it like rock or dirt. This crust is made of iron, not in molten form, but crystallized. Solid. Incredibly strong. A rigid metallic lattice formed under intense gravity. This crust is only a few hundred meters thick, but it's where the star's magnetic and thermal activity interacts with the void of space. And it's dangerous. The magnetic fields here are so powerful that they could erase your credit card from 1,000 kilometers away. In some neutron stars, called magnetars, those fields are 1 trillion times stronger than Earth's. They can bend atoms and rupture molecular bonds. This crust is the battleground of pressures, trying to collapse, trying to escape, trying to keep balance. And it is anything but still. Starquakes, yes, literal earthquakes on the surface of a star, can occur here. They crack the crust, releasing gamma-ray flares that ripple across the galaxy. The inner crust, where physics starts to shake. Just beneath that iron crust lies something stranger. A soup of neutron-rich nuclei suspended in a sea of free-roaming neutrons. Imagine a nuclear ocean, thicker than syrup, denser than steel, suspended under gravity's crushing thumb. As you go deeper, the atomic nuclei themselves start to deform. Squeezed by the weight above, they flatten, twist, and even fuse together into bizarre geometric shapes. Physicists call these formations nuclear pasta. Yes, pasta, spaghetti, lasagna. gnocchi. Not because they're delicious, although strangely comforting, but because the shapes mimic those of the Italian dishes. Long threads, flat sheets, clumps and blobs. These strange states of matter form due to competition between nuclear attraction and the intense repulsion of charged particles being crammed together under pressure. And here's the twist. Some models suggest nuclear pasta may be the strongest material in the universe, 10 billion times stronger than steel. It holds up the crust of the neutron star, resisting cracking, resisting collapse, until one day, it doesn't. The outer core, a neutron superfluid. As we push deeper, the matter becomes more uniform. Here, individual nuclei dissolve. Protons and neutrons flow together into a dense, almost featureless fluid. Except this fluid doesn't behave like anything we know. It's a superfluid, which means it flows with zero viscosity. No resistance, no friction. It can climb walls, it can whirl forever, and it's spinning. Neutron stars are often born spinning rapidly, sometimes hundreds of times per second. As they age, they slow, but that spin stores angular momentum, and the superfluid core can decouple from the crust, spinning at a different rate. Sometimes that spin suddenly transfers back to the crust, a tiny glitch in the star's rotation. We've detected these from Earth, tiny hiccups in the pulses of spinning neutron stars, and they are one of the most direct pieces of evidence that something strange is happening inside. A star with a liquid heart that never stops spinning. The inner core, the unknown frontier. Now we arrive at the deepest layer, the place we know the least about. Theoretical physics begins to stutter here. Is it just neutrons? Do they break down into their component parts? Quarks? Could there be exotic particles here? Hyperons? Kaons? Pions? Some scientists believe the inner core of a neutron star could be a quark-gluon plasma, the same soup that existed just microseconds after the Big Bang. A state of matter where quarks are no longer bound into neutrons or protons, but move freely in a sea of pure force. Others propose strange matter, an ultra-stable form of matter composed of strange quarks that could be so stable it might convert other matter into itself. A hypothetical neutron star made entirely of strange matter would be a strange star, but we've never seen one, not yet. Signals from the deep. We can't drill into a neutron star. We can't scoop its surface or sail its core, but we can listen. Pulsars, spinning neutron stars that emit beams of radiation, act like cosmic lighthouses. As they rotate, their beams sweep past Earth with clockwork precision. Some pulsars are more accurate than atomic clocks, but occasionally they skip a beat, they glitch, they flicker, they shift. Those signals tell us what's happening inside. And in rare cases, a magnetar might unleash a burst of energy so powerful that it briefly outshines every star in its galaxy. One such flare in 2004 hit Earth from 50,000 light-years away. It was powerful enough to ionize our upper atmosphere from that distance. Imagine what would happen if we were closer. Let your imagination wander now to a star so dense it defies all known states of matter, to layers made of pasta, oceans of liquid neutrons, and possibly the raw soup of creation. What lies inside a neutron star is more than mystery. It is a challenge to everything we think we know about matter, gravity, time, and the limits of physics. And yet, they're real. Spinning silently in the darkness, wearing the scars of collapsed giants, and holding the blueprint of the universe's deepest secrets. We left off floating near the crust of a neutron star, gazing into a place where matter has been crushed beyond recognition. But to understand what truly happens inside, we need to spend time with something even more powerful than the star itself. We need to talk about gravity, not just gravity as we know it here on Earth, but gravity so intense that it can bend the fabric of space and time around it. A neutron star's gravity isn't a suggestion, it's a command, a surface you can never stand on. Let's imagine you could somehow float near a neutron star. The first thing you'd notice isn't the star itself, it's what's happening around it. Light bends, time slows. The star, only about the size of a city, warps the space around it so severely that photons, particles of light, don't travel in straight lines. This phenomenon is called gravitational lensing, and it's so strong near a neutron star that you could see the back of the star while facing the front. Light from the far side is bent over the curve, looping toward you. It creates a halo, an illusion, a glowing sphere that defies your normal sense of direction. Try to land? Impossible. The gravitational pull at the surface is 2 by 10 and 11 times stronger than Earth's. You couldn't land on it. You couldn't walk, stand, or even fall normally. You would be flattened instantly into a film of particles. No suit could protect you. No craft could resist that force, and yet, somehow, the star holds together. Its own mass threatens to pull it into a black hole, but its internal pressure resists. This is the razor's edge neutron stars live on, always on the brink of collapse, but not quite tipping over. Time runs differently here. General relativity tells us that the stronger the gravity, the slower time moves. Near a neutron star, time distorts in measurable ways. If you were orbiting just a few kilometers above the surface, 1 minute for you might be several minutes, or even hours, for someone farther away. This isn't science fiction, it's verified. Astronauts on the International Space Station experience this slightly. GPS satellites have to account for it. But near a neutron star, the effect is extreme. You could watch the galaxy spin in fast forward, stars aging while your clock ticks slowly. Time dilation like this is not just a curiosity, it changes how we study these stars. Their magnetic fields decay over time, their pulses slow, but from their own perspective, they age differently. What does it mean to be ancient in a place where time doesn't flow like ours? The equation of state, our greatest unknown. To truly understand what's inside a neutron star, we need one crucial thing: a reliable equation of state. In physics, the equation of state tells us how matter behaves under certain conditions, like pressure and temperature. For water, it tells us when it boils, freezes, or evaporates. For air, it describes how it expands or compresses. But inside a neutron star, we have no complete equation of state. The conditions are so extreme, densities so high, forces so unfamiliar, that our models begin to disagree. Some say the matter becomes a sea of neutrons. Others say it dissolves into quarks. Some think it could even harbour states of matter we've never discovered. Each version gives a slightly different answer for the star's structure. Does it have a soft, squishy core? A hard, crystalline centre? Does it transition in layers or all at once? It's like trying to solve a puzzle when the pieces are made of shadows and starlight. The role of quantum mechanics. While gravity pulls inward, there is another force pushing back: quantum pressure. The particles inside a neutron star obey quantum rules, not classical ones. In particular, they follow the Pauli exclusion principle, which says that no two identical fermions, like neutrons, can occupy the same quantum state at the same time. This principle creates a powerful degeneracy pressure. It's what keeps white dwarfs from collapsing. But in neutron stars, it's even stronger, because we're dealing with neutrons, not electrons. This quantum pressure is invisible, but it acts like a scaffold. It keeps the star from imploding completely. So what you have is a cosmic tug of war. Gravity trying to squeeze everything into a singularity, quantum pressure holding the matter apart, and in the balance between those two forces, a neutron star is born. The limits of mass when a star goes too far. But even this balance has a limit. Add just a little more mass to a neutron star, about 2.3 solar masses, and the quantum pressure can no longer hold it up. The star collapses, no more pulses, no more crust, no more anything. It becomes a black hole. This threshold, the maximum mass a neutron star can have, is called the Tolman-Oppenheimer-Volkoff limit. It's the quantum version of a cliff edge. Past it, physics itself must surrender. We don't know the exact number because it depends on the unknown equation of state, but we think it's somewhere between 2.1 and 2.5 times the mass of our Sun. Some neutron stars sit just below that limit, teetering, balancing, a single spoonful more mass, and they would vanish into the void. The strange case of binary neutron stars. Now imagine two neutron stars orbiting each other, locked in a gravitational dance that lasts millions of years. They spiral inward, slowly, radiating energy in the form of gravitational waves. In 2017, we detected such a collision for the first time. The event was called GW17817, two neutron stars merging 130 million light-years away. What we detected wasn't just gravitational waves. We saw light, gamma rays, X-rays, radio signals. It was a cosmic symphony. From this one event, we learned that neutron stars can merge into black holes. They eject heavy elements like gold and platinum into space. They produce kilonovae, explosions brighter than a supernova, and they confirm that gravity can be used to measure the expansion of the universe. Think of it, the gold in your ring may have come from the death spiral of two neutron stars. The role of neutron stars in the universe. They may be small, they may be rare, but neutron stars shape the universe in quiet, powerful ways. They regulate the chemical evolution of galaxies. They act as cosmic laboratories for high-energy physics. They might even be seeds for the formation of black holes or other exotic objects. And they last. While normal stars may live billions of years, neutron stars could last trillions. Cooling slowly, spinning silently, fading into deep time. There may be billions of them out there, invisible, cold, waiting. Sleeping giants in the darkness. If you flew through space with the lights off, you'd never see one. Neutron stars don't glow like normal stars. They don't cast long shadows or light up nebulae. But if you listened, if you tuned your instruments just right, you might hear a whisper, a flicker, a pulse, and you'd know. Something dense and ancient and strange was passing by. In their silence, neutron stars speak volumes. They carry the story of death and rebirth, of fusion and collapse, of atoms and quarks and the war between gravity and quantum law. They are not just dead stars, they are deep time compressed. They are the universe remembering how to shine, even after its fire goes out. Let's drift now into motion, because not all neutron stars are quiet. Some spin, some flash, some sweep the sky with beams of light like celestial lighthouses. These are pulsars, a special class of neutron stars that rotate rapidly and emit precise beams of radiation. They are among the most accurate clocks in the universe, and they've taught us more about what's inside a neutron star than any telescope ever could. The birth of a beacon. When a massive star explodes in a supernova and leaves behind a neutron star, that leftover core often spins. Why? Because of a law known as conservation of angular momentum. Just like an ice skater pulls in their arms to spin faster, a collapsing star shrinks and spins more rapidly. A star that once rotated once every 10 days might now spin 30 times per second, or even faster. And if the magnetic field survives the collapse, it gets amplified, tangled, compressed, stretched out into enormous loops of invisible force. These magnetic fields funnel charged particles, electrons and positrons, toward the magnetic poles of the star. These particles emit radiation, focused into beams, but the magnetic poles aren't always aligned with the spin axis. So as the neutron star spins, those beams sweep across the sky. If one happens to point toward Earth, we see a flash, a pulse, a cosmic heartbeat. The most accurate clocks in existence. These pulses don't come at random intervals. They come with astonishing precision. Some pulsars are so stable that they rival our atomic clocks. They pulse every second, every millisecond, every microsecond, tick, tick, tick. So perfectly, you could set your watch by them. The fastest known pulsar spins over 700 times per second. That's one rotation faster than the blades of a household blender. Yet this spinning mass is heavier than our Sun, condensed into a sphere the size of a city, rotating at breakneck speed and not flying apart. That alone tells us something about its interior strength. Its structure must be unbelievably rigid. Its gravity must be exquisitely balanced. Its internal layers must flow like nothing we've ever seen. Glitches, when stars skip a beat. But every now and then, the rhythm breaks. Some pulsars experience what physicists call a glitch, a sudden, tiny increase in spin rate. Imagine a star that has been ticking steadily for years, decades, even centuries. And then, in a fraction of a second, it begins to spin slightly faster. Why? Inside the neutron star, the crust and the core aren't always in sync. Remember the superfluid layer? It can spin separately from the crust. When enough pressure builds, perhaps from starquakes or tension in the nuclear pasta layers, the superfluid can suddenly transfer angular momentum back to the crust. It's like a hidden engine giving the outer layers a jolt. To Earth-based detectors, this shows up as a change in pulse timing, a skipped beat, a moment of cosmic surprise, and by studying these glitches, scientists are mapping the behavior of matter at nuclear densities, using stars as laboratories. The lighthouse model and our cosmic perspective. Pulsars aren't the only thing spinning. We are too. Our planet turns. Our solar system orbits the galactic center. Even the galaxy itself spins. So when we detect the pulse of a neutron star, it's like catching a beam of light through layers of swirling motion. We use this information not just to study the stars, but to study space itself. Pulsars help us navigate deep space, measure gravitational waves, test general relativity, and even search for planets around other stars. That's right, planets have been found orbiting pulsars. Dead worlds circling dead stars, bathed not in sunlight, but in pulses of radiation. A strange kind of solar system, alien, ancient, yet bound by gravity just like ours. The pulsar timing array, listening to the universe. Now imagine dozens, even hundreds of pulsars being monitored at once. Scientists have created a network of these cosmic clocks, known as a pulsar timing array. By measuring the tiny shifts in the pulses across the sky, they can detect gravitational waves from some of the most massive objects in the universe. We're not talking about neutron star collisions now. We're talking about supermassive black holes, millions of times heavier than the Sun, locked in orbits after galaxy mergers. These pairs take millions of years to merge, but their gravitational whispers stretch space and time, and those whispers slightly delay the pulses from distant pulsars. By comparing the timing of many pulsars, scientists can triangulate the source of the ripple. Like listening to the way a drumbeat echoes off the walls of a cave, you can tell the shape of the space around you. It's one of the most sensitive experiments in all of physics, and it's powered entirely by stars that died and refused to stop spinning. Pulsars and the shape of the core. These precision measurements give clues about what lies within. For example, if a pulsar spins too fast and its crust isn't strong enough, it could tear itself apart. But the fastest pulsars don't break. That means their cores, possibly made of exotic matter or ultra-rigid neutron lattices, must be incredibly strong. Some theories even suggest that strange quark matter might give them an even more stable spin. That is, if the core transitions into a quark-gluon plasma or strange matter phase, the resulting star could be both denser and more spin-stable than anything else known. So when a pulsar keeps its rhythm for millions of years, it tells us that the matter inside has properties we can barely imagine. It's not just about mass or density anymore. It's about elasticity, structure, geometry. What is the architecture of matter when atoms no longer exist? Magnetars, the monsters among pulsars. And then there are the wild ones. Not all neutron stars are gentle clocks. Some are chaotic, temperamental, and terrifying. These are magnetars, a type of neutron star with magnetic fields so powerful they can rip molecules apart from thousands of kilometers away. A typical magnetar's magnetic field is over 1,000,000,000 times stronger than Earth's. Just to put that in context, if you brought a magnetar as close to Earth as the Moon, every credit card, every phone, every piece of metal would stop functioning. Your own atoms might begin to distort. And when these fields twist and snap, they release giant flares, bursts of gamma rays that can outshine an entire galaxy for seconds. The crust of the star physically cracks, like tectonic plates on Earth, producing starquakes. These flares have been detected from across the galaxy, hitting our atmosphere and briefly disrupting satellites and sensors. And they originate from an object no wider than a city, a neutron star with the heart of a monster. How do magnetars get so strong? One theory is that the magnetic field of the original star is preserved and amplified during collapse. When the core contracts to the size of a city, any magnetic field lines trapped inside get compressed. And just like the star spins faster, its magnetic field gets more intense. In the case of magnetars, this process may be especially efficient, but there may be more to it than just collapse. Some scientists think that internal fluid motions, convection currents, turbulence in the superfluid core, may help maintain or even amplify the field. Others believe there may be phase transitions inside the core, sudden rearrangements of nuclear or quark matter that generate temporary magnetic storms. No one is sure, but what is certain is that a magnetar flare could one day sweep across Earth. And even from light years away, it would be noticeable. Not dangerous, unless it were very close, but noticeable. A reminder that even dead stars can scream. Pulsars in popular science and culture. Because of their precise nature, pulsars have become symbols of cosmic regularity. In 1974, the Arecibo message, a broadcast sent from Earth toward a star cluster, described our location in the galaxy relative to 14 known pulsars. Why? Because their pulse rates are unique and measurable across time. Anyone who detected the message and knew those pulsars could calculate exactly where and when it was sent. In this way, pulsars have become our cosmic timestamps. They're like glowing breadcrumbs we've left in the dark forest of the universe, in case someone, or something, might find us. Even on the Voyager Golden Record, a map of 14 pulsars was engraved. If alien civilizations ever discover the probe, they could trace those signals back to Earth. Pulsars are not just stars, they are coordinates. They are memories. They are the universe keeping time. Tonight, as you fall asleep, think of a lighthouse far away, spinning in darkness, sending beams into the abyss. Not because someone is watching, but because that's what it does. Tick, tick, tick. An immortal heartbeat. A reminder that even in death, stars can guide us home. As we settle deeper into the mysteries of neutron stars, let's shift our gaze from the stars themselves to the legacy they leave behind. One that exists not just in distant galaxies, but perhaps on your finger, in your blood, or in the circuitry of your phone. Neutron stars, especially when they collide, are the universe's forges, factories where the heaviest elements are born. Gold, platinum, uranium, rare earth metals. These elements do not form in the cores of normal stars. Their origin is more dramatic, more violent, and more rare. The alchemy of the cosmos. To make an element heavier than iron, the universe needs a tremendous injection of energy, enough to overcome the nuclear forces that bind protons and neutrons together. Supernovae can provide some of this energy, but even they fall short when it comes to producing the heaviest nuclei. This is where neutron stars come in. When two neutron stars spiral toward each other and merge, they release a colossal burst of energy, along with a tidal wave of neutrons. This neutron-rich environment is perfect for what physicists call the R process, rapid neutron capture. In this process, atomic nuclei are bombarded with neutrons so quickly that they don't have time to decay before more neutrons attach. These overloaded nuclei then decay into stable, heavy elements, some of the rarest and most valuable in the periodic table. It is estimated that a single neutron star merger can produce Earth masses worth of gold and platinum. These elements are then scattered into the interstellar medium, mixed into clouds of gas and dust, and eventually incorporated into new stars, planets, and people. The evidence in our bones. How do we know neutron star mergers create heavy elements? In 2017, when gravitational wave detectors picked up the signal from a neutron star merger, GDID 17817, it triggered a race. Telescopes all over the world turned to the sky. What they saw confirmed decades of theory. A colonnova, a brilliant, short-lived explosion, flared into view. Its light contained spectral fingerprints of heavy elements forming in real time. The brightness, the color, the decay, all matched the models of our process nucleosynthesis. We had witnessed cosmic alchemy, the moment when raw, compressed matter was transmuted into the stuff of rings, satellites, and solar panels. And here's something to think about. The gold in your jewelry, the iodine in your thyroid, the europium in your phone's screen. Some of it may have been born in the moment two neutron stars collided hundreds of millions of years ago, in a galaxy long forgotten. Neutron star mergers as cosmic fireworks. The collision of two neutron stars is not quiet. It begins with a long spiral dance, lasting millions or even billions of years. The two dense remnants orbit each other, losing energy in the form of gravitational waves. The orbit tightens, the pace quickens, faster and faster, until finally they touch. In a fraction of a second, their crusts rupture. Tremendous tidal forces rip pieces from their surfaces. Neutron-rich material is hurled into space, forming glowing arcs of nuclear debris. At the moment of impact, space-time ripples outward, carrying the signature of the event across the cosmos. If the combined mass exceeds the Tolman-Oppenheimer-Volkoff limit, the result is a black hole. Otherwise, the merged object may briefly become a hypermassive neutron star, spinning madly, radiating wildly. before it too collapses. These events are so energetic that they help seed galaxies with essential building blocks. Without them, the universe would be poor in metals. Life as we know it may not even be possible. A matter of rarity. Neutron stars are rare. Binary neutron star systems are rarer still, and mergers, rarer yet. But their rarity is part of their power. Because each event is so productive, so packed with energy and raw material, it makes up for the infrequency. In fact, models suggest that the amount of gold and other heavy elements in our galaxy can be fully explained by neutron star mergers alone. So when you hold a gold coin or wear a platinum ring, you are touching the cooled remains of a cosmic explosion. A stellar fingerprint, a relic of a time when matter danced on the edge of physics and emerged transformed. Earth's cosmic inheritance. The Earth is not just made of ancient rock and molten iron. It's infused with elements from distant stars. Some came from supernovae. Others, especially the heaviest, likely came from neutron star mergers that occurred billions of years before our solar system formed. These elements were part of the dust and debris that coalesced into the Sun and its planets. Our planet's crust, our oceans, even our DNA contains the long-cooled ashes of stars. And so, in a very real sense, neutron stars are part of our ancestry. They shaped not only the chemistry of the cosmos, but the very foundation of life. Galactic recycling. Galaxies are not static. They evolve. Stars are born, live, and die. Their remains, white dwarfs, neutron stars, black holes, continue to orbit, collide, and merge. With each cycle, new elements are forged and new stars inherit the debris. Neutron stars contribute to this galactic recycling. Though small in number, their impact is disproportionate. One collision can enrich an entire star-forming region with rare materials. This chemical enrichment plays a role in the diversity of planets, atmospheres, and ecosystems that follow. It's a reminder that death in the universe is never the end. It's a transformation, a redistribution of energy and matter that feeds the next generation of stars. Echoes of the past. The light from a neutron star merger can travel across the universe for hundreds of millions of years before reaching us. By the time we see it, the collision is long over. But its signature, light, gravity, and matter, still echoes through the cosmos. Telescopes that detect gamma rays, X-rays, visible light, infrared, and radio all contribute to building a picture of these events. Some wavelengths arrive first, others linger, and buried in that data is a map of what was created. Each kilonova we observe adds to our understanding. It helps constrain models of nuclear physics. It tells us what densities are achievable, what elements are synthesized, and how much energy is released. In this way, neutron stars are not just objects. They are time capsules, sending out fragments of their story to anyone patient enough to listen. Listening to the sky. The detectors that first heard the gravitational waves from a neutron star merger, LIGO and Virgo, work not by looking, but by listening. They measure the tiniest tremors in the fabric of space-time caused by distant, violent events. These instruments are so sensitive that they can detect changes in distance smaller than a proton. And yet even that is enough to hear the collision of two stars 100 million light-years away. It's like hearing a whisper in a hurricane, and it means that the universe is not silent. It sings, not in sound, but in gravity, in ripples, in motion. When you lie in bed and feel the weight of the world fall away, know that somewhere out there, space itself is shivering, and that those tremors carry the stories of matter being reborn. The cycle continues. Every time a neutron star is born, a new chapter begins. Every time two merge, a story ends, and becomes the beginning of something else. From their dense cores to their shattered remains, neutron stars are more than relics. They are engines of creation. They defy time, crush atoms, bend light, and shape chemistry. Their collisions forge the rarest materials. Their pulses guide spacecraft and clocks. Their glitches reveal exotic states of matter. And their deaths seed new worlds with the ingredients for life. When you sleep tonight, think of this. Somewhere far away, two ancient remnants are spiraling toward one another. Slowly, silently. They've been approaching for longer than life has existed on Earth. And one day soon, they'll touch. And in a single flash, the darkness will glow with gold. Time will ripple, light will curve, and the story will begin again. Now, let us drift even deeper. Past the outer crust, past the liquid layers, into the darkened center of the neutron star. This is the innermost region, the core of the core, a realm so dense, so alien, that even our most advanced theories begin to unravel. In here, the rules don't just bend, they mutate. The core is a place we've never seen, never touched, and may never fully understand, but it's where the greatest questions lie, and maybe the greatest answers. At the edge of knowledge. What exactly exists at the center of a neutron star? The truth is, we don't know. There are models, guesses, elegant equations that attempt to describe the behavior of matter under these extreme conditions. But the deeper we go, the less certainty we have. At the surface, we can imagine iron atoms in a crystalline lattice. A little deeper, nuclei and neutrons in a quantum sea. But in the core, there may be no individual particles, no protons, no neutrons, just pressure, force, and the raw ingredients of reality. Physics begins to blur here, between nuclear matter, quark matter, and something stranger. Quark soup. One of the most compelling ideas is that the core contains a quark-gluon plasma, a state of matter where protons and neutrons dissolve and their constituent quarks roam freely in a dense, high-energy fluid. In ordinary matter, quarks are trapped in groups of three, like prisoners in a locked cell. But at the center of a neutron star, those walls may vanish. The particles break apart. The quarks float free, accompanied by gluons, the force carriers of the strong nuclear force. This quark soup may be the densest stable material in the universe. It's a form of matter that likely existed just microseconds after the Big Bang, before anything had a name or a shape. In a way, the core of a neutron star may be a time machine, holding on to the earliest form of matter, locked inside the grave of a dead stars. Strange matter. But some theorists believe the core doesn't just contain free-floating quarks, it contains strange quarks. These are heavier versions of the up and down quarks that make up everyday protons and neutrons. Under extreme pressure, strange quarks might emerge naturally, forming strange matter, a hypothetical substance more stable than normal atomic nuclei. And if strange matter does exist, it might spread. It could infect nearby nuclear material, converting it into more strange matter. A neutron star with a core of strange matter might not be a neutron star at all. It might be something entirely new, a strange star. Smaller, denser, stranger. And if a strange star collided with a regular neutron star, the strange matter might convert the entire object. A cosmic chain reaction, a transformation on a stellar scale. It sounds like science fiction, but the physics holds. We just haven't seen it yet. Color superconductors. Go even deeper, and some models predict something even weirder. Color superconductivity. In this hypothetical phase, quarks pair up in exotic ways. forming a kind of frictionless fluid for the strong nuclear force. Just as electrons pair in a superconductor to carry electricity with zero resistance, quarks in this state could carry color charge with perfect efficiency. This state is governed not by magnetism or electricity, but by the strong interaction, the fundamental force that holds atomic nuclei together. It's a reminder that the universe isn't just made of matter and energy. It's made of rules. And sometimes, when those rules are pushed far enough, they behave in ways we never imagined. Pressure without shape. Inside the deepest core, the idea of solid or liquid starts to lose meaning. There is no familiar structure, no atoms, no molecules, just fields and particles and endless pressure. The matter may be so compressed that its properties resemble neither liquid nor gas, but something entirely different, a degenerate state where identity is blurred and boundaries dissolve. Even time and space behave differently here. If you dropped a clock into the core, assuming you could, it would cease to tick. Its hands would freeze, not from cold, but from gravity. Space would twist so severely that distances become meaningless. Time would stretch like fabric under weight. And yet, the star holds, balanced, intact, spinning. Limits of measurement. Everything we know about the neutron star core is indirect. We rely on gravitational wave patterns, thermal emissions, spin rates, and X-ray bursts. We model it on supercomputers. We test theories with particle accelerators by smashing nuclei together and recreating microseconds of high-energy chaos. But none of it is direct. We can't sample the core. We can't drill into it. We can only listen, watch, imagine. This is why neutron stars are so mysterious. They exist in a realm of physics that sits between the known and the unknown, between quantum mechanics and general relativity. And it's in this no man's land that new discoveries await. Black hole or not? One of the biggest debates in astrophysics is whether neutron stars and black holes are two ends of a continuum, or two entirely separate entities. If you add mass to a neutron star, it gets denser, smaller, heavier. But at some point, does it become a black hole suddenly, or gradually? Is there a transitional state between the two? Something we've never seen? A pre-black hole? Or does gravity eventually win all at once, collapsing the core into a singularity? If so, what happens to the exotic matter inside? Does it vanish? Does it remain as a shell around the event horizon? Or does it trigger new physics, something even general relativity can't describe? These questions go to the heart of cosmology, because understanding neutron star cores might help us understand black holes, and that, in turn, may help us understand the fabric of reality itself. The sound of a star. In 2023, astronomers detected the oscillations, literal vibrations, inside a neutron star during a powerful X-ray burst. The star was ringing like a bell made of nuclear matter struck by a burst of energy, humming across space. These vibrations, called quasi-periodic oscillations, carry fingerprints of the star's interior structure. They depend on density, elasticity, shape. By studying them, we might one day deduce the exact makeup of the core. Imagine it, a star, spinning in darkness, humming a sound we can't hear, carrying the key to its own interior, hidden in the pitch and rhythm of its tremors. Why it matters. All of this, the quarks, the gluons, the strange matter, the color superconductors, might seem distant, abstract, like dreams told in the language of physics. But it matters, because inside these stars lie the conditions that mirror the birth of the universe. They hold clues about how matter organizes itself, how gravity behaves at its extremes, how energy can be stored, transferred, and transformed. And more than anything, they remind us that even in death, the universe continues to create, to surprise, to hide things just deep enough that we must stretch our minds and our machines to find them. Tonight, while you rest, know this. Above you, in the stillness of space, there are stars with cores we can't explain. Stars that hold pressure greater than any on Earth. Stars whose hearts may be made of the same raw essence that once filled the newborn cosmos. They don't shine brightly, they don't call attention, but they spin, they pulse, they endure, and one day they may give up their final secrets. Let's shift our focus now, not from the heart of the star, but back toward its skin. The crust of a neutron star might seem thin, just a fragile shell atop a monstrous core, but it's one of the most extreme and mysterious layers in the universe. It isn't just a passive surface. It bends, it shifts, it cracks, and when it breaks, the entire cosmos listens. These events are called starquakes, and they are the tremors of giants. Tonight, we'll drift into that rigid shell where pressure builds silently until the unthinkable happens. The crust, a solid like no other. The outer crust of a neutron star is believed to be a few hundred meters thick, but what it lacks in depth, it makes up for in strength. It's a rigid, crystalline lattice of ions, compressed so tightly by gravity that it forms one of the hardest materials in the universe. This crust is not stone, it's nuclear iron, a dense, incredibly ordered structure where electrons are stripped from atoms and packed into a sea of degenerate particles. Even the deepest mines on Earth are playgrounds compared to this place. The crust resists the tremendous inward force of gravity while holding back the intense magnetic pressure from within. And eventually, that pressure overwhelms the structure. The breaking point. Over time, stresses build in the crust. Magnetic fields twist and shift like roots writhing underground. Rotation slows, mass redistributes, and the internal layers move. The crust can only hold so much tension. Then, without warning, it snaps. A starquake is born. It's not just a crack. It's not just a vibration. It's the sudden realignment of the star's outer shell. And it releases a staggering amount of energy, enough to send gamma rays surging into space, enough to throw off the star's rotation by measurable amounts, enough to briefly alter the very structure of space-time around it. We've recorded these. In December 2004, a starquake from a magnetar 50,000 light-years away hit Earth. It was so intense that it briefly compressed our upper atmosphere and overwhelmed satellites with radiation. And that was from a star we could barely see, halfway across the galaxy. Imagine standing on a world orbiting closer to that event. You wouldn't just see the flash, you'd feel it in your bones. Starquakes and magnetars. Most violent starquakes come from magnetars, the most magnetic neutron stars known. Their magnetic fields are so strong, they can deform the crust itself, warping it from within. The tension these fields generate is enormous. When the crust finally yields, the magnetic field snaps back like a stretched rubber band suddenly released. This produces a flare, short, sharp, and dangerous. We call them soft gamma repeaters, but there is nothing soft about them. They are some of the most energetic events in the known universe. These flares are often followed by aftershocks, tiny pulses that ripple through the star like a bell that's just been struck. Studying these pulses reveals information about the star's internal structure, like seismology for a star. Starquakes and rotation glitches. Sometimes, after a starquake, the neutron star begins spinning faster. These sudden speed-ups are called glitches, and they tell us something crucial. The crust and the core are not perfectly coupled. Inside the neutron star is a superfluid, frictionless, flowing, and separate from the crust. When the crust cracks, it can shift angular momentum with the core, causing the entire star to rotate differently. It's as though the star coughs, and its rhythm changes. Astronomers track these glitches with extreme precision. They help map out the strength and composition of the crust. They also offer rare glimpses into the behavior of exotic matter: neutron superfluids, quantum vortices, and nuclear pasta beneath the surface. The sound of the crack. Can you imagine the sound of a neutron starquake? Of course, space is silent. There's no air to carry vibrations. But if there were, the sound would be deep, alien, a single rupture releasing pressure that's been building for millennia. Scientists sometimes simulate these events with computer models. The waves that follow a starquake create a kind of resonance inside the star. By measuring how those waves travel, we learn about the star's density, structure, and core composition. Just like we use earthquake waves to study the Earth's interior, we can use starquake waves to study the inner life of neutron stars. It's a method called asteroseismology, listening to stars through their quakes. Each crack is a clue. Crustal mountains. You might think a star this massive would be perfectly round, but neutron stars can have mountains, tiny deformations in the crust caused by stress and uneven pressure. But remember, these aren't mountains like Everest. They're only a few millimeters tall, but on a neutron star, that's enough. Even the tiniest bump creates a distortion in the star's gravitational field. And if the star is spinning, that bump becomes a wobble, a ripple in space-time that can be detected by gravitational wave observatories. These mountains, just grains compared to the size of the star, carry immense information. They may even produce continuous gravitational waves. Not bursts, not collisions, but a steady signal, humming from across the galaxy. Detecting that signal would let us map the star's surface, not through light, but through gravity, through the way space itself bends and shifts around the star's shape. Long-term evolution of the crust. As neutron stars age, their crusts change. Young neutron stars cool rapidly. Their magnetic fields may twist and decay. Their rotation slows. Cracks form. Layers shift. Starquakes become less frequent, but not less violent. Some neutron stars may enter quiet phases, where the crust becomes rigid and unchanging. Others may continue to pulse and twitch for millions of years, flickering reminders of internal unrest. In some models, the crust eventually breaks down entirely, blending with the superfluid core. In others, the magnetic field decays so completely that the star becomes invisible, cold, dark, and quiet. A black neutron star drifting through the galaxy in silence. But even then, the crust holds its secrets. It is a fossil, a layer built from pressure, fire, and the strange rules of quantum matter. And it may outlast everything else. The tension between stillness and collapse. What makes the crust so fascinating is the tension it embodies. It is the outermost layer of one of the most extreme objects in existence. It should crumble, it should collapse, but it doesn't. Instead, it holds until it doesn't. And in that single moment of surrender, in the crack, the quake, the flare, it reminds us how much energy can be stored in silence, how much pressure can live inside stillness, and how fragile even the strongest materials become when pushed far enough. That paradox, strength on the edge of collapse, is written into every inch of a neutron star's crust. Tonight, as you lie still, know this. Above you, in the vast black sea of space, stars are shaking. not in chaos, but in pattern, in rhythm. Their quakes are not signs of weakness, but of memory, of history, of pressure finally released. A neutron star is not a monument, it's a living scar, one that remembers every layer of its past and every force that shaped it. And when it cracks, the universe listens. In the stillness of space, where silence stretches for light years and time slows beneath immense gravity, neutron stars offer something unexpected: order, rhythm, precision. They are not just strange remnants of stellar death, they are clocks, libraries, navigational beacons. Their very existence helps us measure the universe, its age, its motion, even its shape. Let's explore how these dense, spinning orbs became the most accurate timekeepers we've ever known. Timing in a chaotic universe. Our cosmos is not as chaotic as it seems. Beneath the swirling galaxies and tumbling comets, there are systems of great regularity. Among them, pulsars, a type of neutron star, stand out. These are neutron stars that emit beams of electromagnetic radiation. As they spin, their beams sweep across space like a lighthouse. If Earth lies in the path of one of these beams, we see a steady, repeating pulse. Some of these pulses arrive with such regularity that they rival the most advanced atomic clocks. For decades, astronomers have used these stars to keep time, not just on Earth, but across the cosmos. Millisecond pulsars, the galactic metronomes. Among pulsars, the most precise are called millisecond pulsars. These are neutron stars that spin hundreds of times per second. Their periods are stable, impossibly stable. Some don't vary by more than a few microseconds over decades. They didn't start out this way. These stars were likely once regular pulsars that slowed down, until they were spun up again by accreting matter from a binary companion. As the gas fell onto the neutron star, it transferred angular momentum, causing the star to accelerate its rotation. What results is a kind of cosmic metronome, a spinning star that pulses with such stability we can use it to track time on Earth, and even detect tiny ripples in space-time. Pulsar timing arrays. Using an entire array of millisecond pulsars across the sky, scientists have created something called a pulsar timing array, a galactic-scale observatory. Imagine dozens of pulsars scattered across the Milky Way, each pulsing in perfect rhythm. By monitoring their arrival times with extreme accuracy, astronomers can detect subtle distortions caused by gravitational waves. These aren't the brief, sharp waves from neutron star mergers. These are the long, slow ripples from orbiting supermassive black holes, objects so huge they warp the galaxy around them. As these giants orbit each other, they stretch and compress space. The pulsars tell us when that happens, not with sound, not with light, but with timing. Delays so small they are measured in billionths of a second. It's a kind of gravitational whisper, and pulsars, like ancient ears, are always listening. Mapping space with stars. We've also used pulsars to help define our place in the universe. On the Voyager spacecraft, a golden record was engraved with a map, showing Earth's position relative to 14 known pulsars. Each line includes the frequency of the pulsar's pulses, encoded in binary. Why pulsars? Because they are unique. Each has its own pulse rate and position. If someone, somewhere, were to find that map, they could trace those stars backward and locate us, even if it took millions of years. In this way, neutron stars are not just timekeepers. They're lighthouses, beacons, anchors in the sea of the cosmos. A galactic calendar. Because pulsars lose energy over time, their spin slows. This slowing is predictable. By studying it, astronomers can estimate a pulsar's age. Some are newborns, only a few thousand years old. others are ancient, billions of years in quiet rotation. These ages help map the history of our galaxy, where stars lived, where they died, how the Milky Way has evolved. It's as if each pulsar is a ticking clock buried inside a fossil, not just telling us the time, but the story of time itself. Testing Einstein. Pulsars are more than timers. They are laboratories for testing the laws of physics. In particular, Einstein's theory of general relativity. In binary systems, where two neutron stars orbit each other, or a neutron star orbits a white dwarf, we can study the effects of gravity with incredible precision. Relativity predicts how the orbits should decay, how time should dilate, how space should curve, and pulsars confirm these predictions again and again. In some systems, we've even seen gravitational waves cause the stars to spiral inward, exactly as Einstein said they would. It's a rare thing to test a theory of the cosmos using the corpses of dead stars, but neutron stars allow it, because they are not just objects, they are instruments. Natural navigators. Imagine a future spacecraft far from Earth, too distant for GPS, out of contact with ground stations. How would it navigate? It could use pulsar navigation, a real developing technology that uses the timing of pulsar pulses to determine position in space. Just as sailors once used stars to find their way, future explorers may use neutron stars. Compact, precise, and ever reliable, they could form a celestial grid, guiding us through the void. Even today, NASA has tested this concept with the sextant experiment aboard the ISS. It's the first step toward interstellar navigation powered by dead stars. Beyond human clocks. Our best clocks, atomic clocks, are remarkable. They keep time by measuring the vibration of atoms like cesium or hydrogen. But pulsars, especially millisecond pulsars, offer a different kind of stability. Not limited by human engineering, not confined to a lab, they pulse naturally. Across millions of years, across thousands of light years. And while they may drift or glitch, they do so with rules, patterns, predictable behaviors. As our understanding of the cosmos grows, we may begin to sync our systems, not just to Earth's rotation or atomic vibrations, but to the stars themselves. Clocks made of collapsed suns, timers etched in gravity, memory carried in motion, a timekeeper's legacy. Each neutron star is the end of a life, a star that lived, burned, exploded, and collapsed. And yet in death, it found purpose. It became more than matter. It became structure, order, a keeper of rhythm in a universe that often seems random. The very rotation of a neutron star is a leftover dance, a remnant of momentum from a supernova long past. And as it turns, it becomes a calendar, a compass, a message. What does it mean that we, fragile and warm-blooded beings, rely on the frozen corpses of stars to mark our time? Perhaps it means that time itself is a gift of death, that every second we count is borrowed from a star that ended, and that every moment we live is measured in pulses from something that no longer breathes, yet never stops moving. Tonight, as the world slows and silence falls, remember this. Far above, scattered across the sky, stars are ticking. Not to rush you, not to measure your days, but to sing a song of continuity, of stillness and motion, of endings that became beginnings. Neutron stars do not age the way we do, but they remember, and through their rhythm they keep the memory of the cosmos alive. In the quiet dark of the cosmos, where individual stars flicker in silence, some are not alone. Some live in pairs, bound not by choice but by gravity. And among these pairs, neutron stars perform their most breathtaking dances. Tonight, we enter the world of binary systems, where neutron stars share their lives with other stars, orbiting, colliding, and transforming in ways that illuminate the mysteries of mass, magnetism, and motion. The power of pairs. Most massive stars are born in multiples, so when one of those stars reaches the end of its life and collapses into a neutron star, the other often remains: a white dwarf, a regular star, or even another neutron star. These stellar duets can last millions of years. Their orbits gradually decay, and what happens between them can shape galaxies. Some of the most dramatic cosmic events, supernovae, kilonovae, bursts of X-rays and gamma rays, emerge from binary systems. Neutron stars in pairs are not just survivors, they are storytellers. Feeding the beast, accreting neutron stars. In a typical binary system, one star may remain in a normal state, hydrogen-rich, burning steadily. The neutron star, meanwhile, becomes a cosmic scavenger. Its gravity is so intense that it can siphon matter from its companion, forming an accretion disk around itself. As the gas spirals inward, it heats up, reaching temperatures of millions of degrees. This hot plasma emits X-rays, and the system becomes what we call an X-ray binary. We can observe these systems from Earth. They flicker and pulse with high-energy light, revealing the neutron star's spin, magnetic field, and appetite. In some cases, the accretion becomes unstable. The neutron star's surface ignites in a burst of nuclear fusion. We call these X-ray bursts, brief flashes that outshine the sun by orders of magnitude. They last seconds, but carry the fingerprints of the star's crust and core. It's a feast of physics, a feeding frenzy written in radiation. The spin-up effect. As matter falls onto the neutron star, it brings with it angular momentum. Over time, this causes the neutron star to spin faster, a process known as recycling. This is how we get millisecond pulsars. Old neutron stars spun up to incredible speeds by millions of years of accretion. These spun-up stars become galactic timepieces, pulsing with unmatched regularity. Their stories began in chaos, but they end in precision. It's one of the strangest transformations in astrophysics. A dying star becomes an atomic clock. Neutron star binaries. Sometimes both stars in a binary system collapse into neutron stars. These double neutron star systems are incredibly rare, but deeply important. Over millions of years, they spiral toward each other, their orbits decaying due to the emission of gravitational waves. When they finally collide, the result is a kilonova, an explosion that produces gold, platinum, and other heavy elements, along with gravitational wave signals that travel across the universe. We detected one of these mergers in 2017, GW170817. It was the first time we saw light and gravitational waves from the same event. It confirmed theories about the origin of heavy elements and gave us new tools to measure the expansion rate of the universe. Two dead stars locked in orbit gave us more than beauty. They gave us clarity. Neutron star black hole binaries. In even rarer systems, a neutron star orbits a black hole. These are cosmic tightrope acts. The neutron star is dense, but the black hole is denser still. If they merge, the black hole often swallows the neutron star entirely, leaving little trace. But if the neutron star is torn apart before it crosses the event horizon, it can release a flare of radiation, a final gasp, a farewell. These events are difficult to detect, but as gravitational wave observatories improve, more of these unions will be found. Each one is a meeting of opposites, the densest matter in the universe versus the deepest void. Together, they shape space-time in waves we're only beginning to understand. Evolution of binary systems. Binary systems are not static. As the stars orbit, they change each other. Mass is transferred, orbits shrink, magnetic fields twist, radiation blasts out. The system evolves over millions or billions of years, often ending in a spectacular death or in a quiet, stable pairing. Some neutron star binaries will never merge. They will spin forever, like celestial dancers locked in a frozen waltz, pulsing steadily until the universe grows cold. Most stars shine with light, some pulse with rhythm, but a rare few command magnetism. These are magnetars, the most magnetic objects known in the entire universe. Born from the same collapses that create neutron stars, magnetars are a different kind of aftermath. Their magnetic fields are so strong, they can twist atoms, tear open crusts, and unleash bursts of radiation more powerful than a billion suns. Tonight, we'll drift into the strange and volatile world of magnetars, where the very fabric of matter is stretched by invisible forces, and the rules of physics bend in unexpected ways. A magnetic field beyond imagination. Earth has a magnetic field. It shields us, shapes our auroras, and helps animals migrate. But the field of a magnetar is not a gentle blanket, it is a storm. A magnetar's magnetic field can be up to 1,000 trillion times stronger than Earth's. That's so intense it can distort the shape of atoms. It can create vacuum polarization, where empty space behaves like a lens, bending light without needing matter at all. If a magnetar were placed halfway to the moon, its field could wipe the data on every credit card on Earth. But don't worry, it's very far away. Most known magnetars live deep in the Milky Way, silent and dangerous. Their violence is rare, but unforgettable. How magnetars form. Magnetars are thought to form in a very specific kind of stellar death. When a massive star explodes in a supernova, if its core collapses rapidly and rotates quickly, it can generate a dynamo effect, a cosmic engine that amplifies magnetic fields beyond all reason. Within seconds, a neutron star is born, but one unlike the rest. Instead of a relatively calm pulsar, the baby neutron star becomes a magnetar, seething with energy, its field twisting around it like a snake of invisible force. This field doesn't just exist, it acts. It warps the crust, it stresses the surface, it builds pressure beneath the rigid shell, until the inevitable happens. The bursting beast. When the magnetic pressure becomes too great, the crust of the magnetar cracks. This is a starquake, and with it comes a magnetar flare. In 2004, one of these flares reached Earth from a magnetar called SGR 1806-20, 50,000 light-years away. The burst lasted less than a second, but in that instant it released more energy than the Sun produces in 100,000 years. Satellites around Earth were temporarily blinded, the ionosphere compressed, and yet this was only a whisper of what magnetars can do. These flares come in several forms: short, repeating bursts, or giant flares, the most violent stellar events this side of a supernova. And after the flare, the magnetar often quiets again, its energy spent, until the next time its crust can no longer hold. The soft gamma repeaters. Some magnetars are known as soft gamma repeaters, SGRs. They emit frequent, low-energy gamma-ray bursts. These bursts are not lethal to life at Earth's distance, but they are markers, beacons of stellar unrest. SGRs tend to flare unpredictably. They might remain dormant for years, then suddenly awaken with multiple outbursts in the span of hours. It's as if the star has seasons of silence and fire. Astronomers track these events closely, not just for their beauty, but for their clues. The light curve, the afterglow, the vibrations. Each flare teaches us more about the star's magnetic interior. Every burst is a glimpse into the invisible. Anomalous X-ray pulsars. Other magnetars are called anomalous X-ray pulsars, AXPs. They pulse regularly, but their energy source is not rotation, as it is in most pulsars, but magnetic decay. In a typical pulsar, the spin slows down and the pulses fade. But in AXPs, the star remains bright in X-rays long after it should have dimmed. Why? Because the magnetic field is decaying, leaking energy into the star, heating it from within, and keeping it active. It's like a furnace that burns without fuel. The magnetism itself powers the glow. These stars challenge our understanding. They defy models, and they remind us that even among neutron stars, there are exceptions, wild cards that break the mold. Magnetic field decay and evolution. A magnetar doesn't remain powerful forever. Over tens of thousands of years, its magnetic field decays. The crust may settle, the flares become rarer, the star grows quiet. Eventually, it may resemble a regular neutron star, indistinguishable from its calmer cousins. But inside, it retains a history written in stress and radiation. Some theorists believe that many neutron stars we now consider normal may have once been magnetars. Their fields faded, their bursts ended, their hearts cooled, but the scars remain. It's a slow transformation from fury to silence. Magnetic atmospheres. The surface of a magnetar isn't like any other star. Its atmosphere, thin as it may be, is warped by its field. Photons, particles of light, don't travel in straight lines. The magnetic field splits them by polarization. Some photons are absorbed, others are deflected. Some even change direction, tracing spirals through the field. In these magnetic atmospheres, ordinary physics breaks down. Light does things it can't do elsewhere. Matter behaves in quantum ways, guided more by field strength than by temperature. Even space itself bends to the will of the magnetar. Could magnetars threaten Earth? From their great distances, magnetars pose no threat to Earth. The radiation from a flare would be dangerous, and only if a magnetar were very close, within about 10 light years. Thankfully, none are that near, but they serve as reminders of power, of potential, of what lies sleeping in the dark. The universe is not always calm. Sometimes it hides giants that breathe fire in silence, and we are lucky to see them from afar. Why magnetars matter? Magnetars are not common. Of the thousands of known neutron stars, only a few dozen are confirmed magnetars. But their rarity makes them precious. They offer laboratories for extreme physics, tests of quantum electrodynamics, general relativity, nuclear structure. They show us how matter behaves under pressures we cannot recreate on Earth. And perhaps more importantly, they show us contrast. For in a sky full of regularity, magnetars are wild. While pulsars tick, magnetars scream. While others pulse in calm rhythm, they burst in unpredictable flame. They are the jazz players of the stellar world, improvised, unstable, brilliant. The beauty in unpredictability. Not everything in the universe follows a perfect pattern. Not all stars die quietly. Some resist their fates. Some erupt. Some linger in states of imbalance, twisting under their own intensity. Magnetars remind us that even in death, there can be unrest. That stillness is not always silent. That even collapsed matter can rise again, if only for a moment, in a burst of unstoppable energy. And as you drift into sleep, remember this. Out there, among the stars, are ancient corpses filled with magnetic storms. They spin, they strain, they crack, and when they do, they light up the galaxy. Not for attention, but because they must. Because their very nature cannot be contained. We've spoken of fire and force, of magnetism and matter collapsing in on itself. But beneath all of that, beneath the crust, beneath the noise, there is a hidden world, quiet, fluid, quantum. Tonight, let's drift into the core of a neutron star not as explorers, but as dreamers. We'll follow the smallest building blocks of nature into the densest realm we've ever imagined, where physics becomes poetry and matter forgets it ever had a shape. Inside the core, a quantum ocean. At its center, a neutron star is not a solid sphere. It is believed to be more like an ocean, one without waves, without light, without temperature in the way we understand it. It is an ocean of neutrons, uncharged particles that normally exist in atomic nuclei, now free from the confines of atoms. They move as a superfluid, a state of matter with no friction, no resistance, and no boundaries between motion and stillness. In this heart, matter flows like thought. It does not obey classical physics. It obeys quantum mechanics, where particles behave more like possibilities than points. Superfluidity, the perfect flow. Imagine a liquid that can climb the walls of its container, a fluid that spins endlessly without ever slowing down. That's what superfluidity is. On Earth, we've created superfluids in laboratory conditions using helium cooled to nearly absolute zero. But inside a neutron star, the superfluid forms naturally, not from cold, but from density, from pressure so intense it pushes neutrons into perfect alignment. This neutron superfluid isn't cold. It's hot by our standards, millions of degrees. But in quantum terms, it behaves as if it were chilled to near zero. It flows without losing energy. It spins in discrete vortices, quantized whirlpools of motion anchored to the star's crust. When the crust cracks during a glitch or quake, the vortices shift, and the entire rotation of the star can change in a sudden jump. That's quantum behavior on a stellar scale. Superconductivity, a star that conducts without resistance. Alongside the superfluid of neutrons may exist a superconducting sea of protons. These charged particles, when paired in the right quantum configuration, allow electric currents to flow without resistance. Together, these two quantum states, superfluid neutrons and superconducting protons, coexist in a bizarre harmony. They shape the magnetic fields, they stabilize the spin. They may even transmit vibrations that ripple through the star like a ghostly bell. This core may be the quietest place in the universe, and one of the most dynamic. Ghost particles, the role of neutrinos. As a neutron star forms and cools, it sheds heat in the form of neutrinos. Tiny, nearly massless particles that rarely interact with matter. In the first few minutes after formation, a neutron star emits an astonishing number of these ghost particles. They carry away energy, cooling the star more rapidly than radiation ever could. Neutrinos pass through walls, through planets, through you. But in the heart of a neutron star, they are born in abundance, created in fusion, decay, and annihilation processes, each one a whisper from the heart of a dying star. Even now, ancient neutron stars continue to emit a trickle of these particles, a silent flow of ghosts drifting through space, carrying stories in silence. Vortex lines, quantum threads of motion. Within the neutron superfluid, rotation doesn't happen the way it does in normal fluids. Instead, it forms vortex lines, tiny thread-like tubes of quantized angular momentum. These lines are anchored in the star's interior. They dictate how the star spins. If they shift suddenly, due to crustal motion or magnetic changes, the entire star's rotation can glitch. It's as if the star's heart is stitched with invisible thread, and every pulse is a tug on that thread. These vortex lines may also interact with the crust, pinning and unpinning as the star evolves. Their behavior is part of why pulsars behave the way they do, why they spin with such reliability, until they don't. Pastaphases, the weird shapes of matter. As we move outward from the core, the matter becomes less uniform. In the inner crust, nuclear material may take on bizarre shapes, called nuclear pasta. Under pressure, the protons and neutrons in this region organize themselves into spaghetti-like strands, lasagna-like sheets, and gnocchi-like blobs. These aren't metaphors. That's how physicists describe them. These structures arise from the competition between nuclear attraction and Coulomb repulsion. They represent the most efficient packing of nuclear matter just on the edge of becoming a uniform fluid. The result is the strongest material in the universe, stronger than graphene, stronger than diamond. These pastaphases help the crust resist cracking until the strain becomes too great. Matter without identity. In these depths, particles begin to lose their identity. Neutrons become indistinguishable. Quantum states overlap. The idea of individual particles fades. What remains is a collective behavior, an emergent property of quantum statistics. It's not what each particle is doing, it's what the whole system is doing. It's like a symphony where no single instrument can be heard, only the music they make together. That's the heart of a neutron star. Simulations on Earth. We cannot drill into a neutron star. We cannot reach its core, but we can simulate aspects of it in particle accelerators by smashing heavy ions together at near light speed. These collisions recreate temperatures and densities for tiny moments where matter melts into quark-gluon plasma, where the early conditions of the universe flicker back into being. By studying these collisions, we learn what neutron star cores might contain, not directly, but by analogy, like studying firelight to understand the sun. It is imperfect, but it is something. The limits of knowledge. Despite all our models, all our equations, the core of a neutron star remains a mystery. It is the most extreme stable form of matter that exists, balanced on the edge of collapse, yet somehow not falling. We cannot see it, we cannot touch it, but we can imagine it, and in that imagining, we build understanding. Perhaps someday a neutron star will come close enough, or reveal itself through gravitational waves or quantum echoes, that we can truly listen to its heart. Until then, we dream, we model, we wait. And in the meantime, the universe continues to hide its deepest truths in these silent cores. A core of wonder. What's inside a neutron star? The simplest answer is neutrons, but the real answer is stranger. It's a fluid that flows without resistance, a conductor that carries charge without heat, a heart that beats without sound, a storm that never moves, and yet turns entire galaxies with its gravity. It is both the end of a life and the seed of the next. It is silence shaped by force, matter that has forgotten itself, a poem written in quantum states, spinning endlessly through the void. And so, as your mind drifts further tonight, let yourself imagine a star collapsed into itself, its crust cracked, its core flowing in secret harmony. No eyes see it, no wind stirs it, but it spins and it sings, and its song echoes across 1 billion years of time. You can't hear it, but somewhere the universe does. Neutron stars live long lives, spinning, pulsing, glowing softly in the silence of space. But sometimes these lives end not in isolation, but in union. A collision, a cosmic embrace that reshapes matter, light, and time itself. Tonight, we'll witness what happens when two of these stellar remnants spiral together. We'll fall into the ballet of death that creates some of the most precious elements in the universe and sends ripples through the very fabric of space. The spiral begins. Imagine two neutron stars orbiting one another. They were once massive stars, born in the same nursery. They lived, they burned, they died. And now their remnants are locked in orbit, slowly, inevitably spiraling inward. Why? Because of gravity, but not just gravity in the way we feel it here on Earth. This is gravitational radiation, energy leaking from the system as ripples in space-time. These ripples carry away momentum, shrinking the orbit. Each year, each millennium, they draw closer. Their orbit quickens, their pulses grow shorter, until finally the stars are spinning around one another hundreds of times per second. The collision is near. A flash across the cosmos. Kilonova. When the two neutron stars finally merge, the event is explosive. Not just violent, not just bright, but something entirely new. A kilonova. Unlike a supernova, which forms a neutron star, a kilonova is what happens when two neutron stars come together. Their collision ejects massive amounts of neutron-rich material into space, where it undergoes rapid nuclear reactions, forging the heaviest elements known to science. Gold, platinum, uranium, rare earth elements, all born in a flash that lasts only hours or days. For centuries, we searched for the source of these elements. Now we know they were born in stellar death spirals. The next time you see gold on a ring, a satellite, a circuit board, remember, it came from a neutron star collision billions of years ago. The 2017 event, GW 170817. In August 2017, astronomers witnessed the first kilonova in history using both light and gravitational waves. The event was called GW 170817. Two neutron stars, 130 million light-years away, collided. First, LIGO and Virgo, the gravitational wave observatories, detected the ripples in space-time. Then, just 2 seconds later, a burst of gamma rays arrived. Telescopes around the world turned toward the source. They watched a kilonova bloom in real time. Blue at first, then fading to red. Heavy elements rained outward. The afterglow lasted for months. It was the dawn of multi-messenger astronomy, a new way of understanding the universe through both light and gravity. and it confirmed that neutron star mergers are the factories of the cosmos. What happens after the collision? What forms after a neutron star merger depends on the combined mass of the two stars. If their total mass exceeds a certain limit, the result is a black hole, a singularity wrapped in an event horizon where not even light can escape. If their mass is lower, the merger may create a hypermassive neutron star, a super-spinning, ultra-hot, unstable object that shines briefly before collapsing under its own weight. Some scientists believe these hypermassive stars might persist for seconds, minutes, or longer, depending on their magnetic support. In that short time, they may emit jets of energy, launching gamma-ray bursts into space. Others may form stable neutron stars, newly born from collision, heavier, hotter, and infused with fresh spin. The outcome is a mystery, but the process is a gift, giving us light, elements, and gravitational signatures all at once. The role of jets and disks. In the moments after a neutron star merger, a swirling accretion disk forms around the central remnant. Jets of material are launched from the poles, blazing beams of gamma rays that can stretch across galaxies. These short gamma-ray bursts last less than 2 seconds, but carry unimaginable power. They're among the most luminous events in the universe. We detect them as flashes of high-energy radiation, sometimes followed by a kilonova glow. Together, these signatures help us confirm the details of the merger: the angles, the masses, the rotation speeds. Each piece of data tells us more about what lies inside the stars, not just their surfaces, but their hearts. Tidal forces and star deformation. As neutron stars approach collision, they deform. They stretch under each other's gravity, pulling tidal bulges just like the moon does to Earth's oceans, but far more violently. These tidal effects influence the gravitational wave signal. By studying the wave's shape, scientists can infer the tidal deformability of the neutron stars. This tells us something profound: how soft or stiff the neutron star matter is, how compressible it is, whether it behaves more like fluid or crystal, whether it holds exotic matter within. In this way, each collision becomes an X-ray of matter itself, revealing secrets no lab could ever reproduce. Seeding the cosmos. The material flung out from the merger spreads into space, eventually mixing with gas clouds. These enriched regions may one day collapse into new stars, new planets, and maybe even new life. Our Earth is such a place. Our gold, our rare isotopes, our very atomic complexity, all trace back to ancient stellar collisions. Without neutron star mergers, the periodic table would be incomplete. Biology would lack the ingredients for complexity. Civilization, as we know it, would never form. We are, in a very literal sense, the aftermath of stellar collisions. Gravitational waves. Space speaks. The discovery of gravitational waves from neutron star mergers is one of the greatest achievements of modern science. These ripples carry information no light can. They travel unscattered through dust and gas. They stretch and squeeze space itself. By listening to them, we measure the universe's expansion rate. We test general relativity. We map the life cycle of stars. And in each signal, we hear the echo of a dance that ended millions of years ago, but whose waves only just reached us, like a message in a bottle, floating across the sea of time. The rarity of collisions. Neutron star mergers are rare. In a galaxy like ours, they may happen only once every 10,000 to 100,000 years. But when they do, they change everything. With better detectors and wider surveys, we're finding more. Some may involve black holes, some may show entirely new physics, others may challenge our models of matter and gravity. Each collision is a gift, a lesson, a question answered, and a new one asked. Sleep under a sky of collisions. As you rest tonight, imagine the quiet sky above you. Calm, still, stars twinkling in the distance. But behind that stillness, across vast stretches of space, collisions are unfolding. Stars are spinning toward their end. Matter is heating, stretching, breaking, fusing. And from that fire, gold is born. Light is released. The universe reshapes itself, quietly, beautifully, eternally. We may never witness a merger with our own eyes, but the light and gravity it sends will find us. It already has. You are stardust, yes, but not just any dust. You are the dust of neutron stars. You are made from cosmic collisions, written in gravitational song. And the universe remembers you. Beneath the serene glow and rhythmic pulse of a neutron star lies a landscape unlike anything on Earth. The crust, a thin but incredibly strong shell, forms the boundary between the quantum ocean inside and the vastness of space outside. Though it may seem solid, the crust is a realm of extremes. Immense pressure, exotic structures, and forces so intense they warp the very nature of matter. Tonight, we explore this outer layer, where atomic nuclei arrange themselves in strange patterns, and where the star's surface tells a story of ancient violence and ongoing tension. The thickness of the crust. Though a neutron star can be roughly 20 kilometers in diameter, its crust is surprisingly thin, only about 1 to 2 kilometers thick. But in those few kilometers, the density jumps from normal atomic scales to several billion times that of Earth's densest metals. Imagine compressing the entire human population into a sugar cube, or a mountain squeezed into the volume of a teaspoon. This layer holds the key to the star's stability and behavior. It is both brittle and strong, cold and hot, simple and complex. Layers within layers. The crust is composed of two main regions, the outer crust and the inner crust. The outer crust consists of a lattice of nuclei, ions packed tightly, bathed in a sea of electrons. This region looks like an ultra-dense crystal, but these aren't atoms as we know them. They are neutron-rich, heavy nuclei, squeezed together by the crushing gravity. Deeper, the inner crust grows stranger. As pressure rises, some neutrons escape their nuclei and roam freely, forming a neutron fluid that coexists with the nuclear lattice. This coexistence is unique, solid and fluid, separate yet intertwined, a dance of matter unlike any on Earth. Nuclear pasta, strange shapes of matter. One of the most fascinating features of the inner crust is the existence of nuclear pasta. Exotic structures where nuclear matter forms shapes resembling lasagna sheets, spaghetti strands, or even gnocchi blobs. These bizarre forms arise because of competing forces. The strong nuclear force pulls protons and neutrons together, while the electromagnetic force pushes protons apart. The result? Matter that organizes into the most efficient, yet strange, arrangements imaginable. This nuclear pasta is believed to be incredibly strong, perhaps the strongest material in the universe, supporting the crust against the immense gravitational pressure. The crust's role in starquakes. Though incredibly tough, the crust is not unbreakable. Over time, stresses build up due to the star's rotation slowing and magnetic fields twisting. Eventually, the crust cracks in a sudden event called a starquake. These quakes can change the star's rotation, producing sudden glitches in pulsar timing. They may also trigger magnetar flares, releasing bursts of radiation into space. Though unseen, these starquakes echo through the star's interior and beyond, reminding us that even the densest matter can fracture and shift. Surface phenomena, the star's skin. The outermost layer of the crust is what we call the surface or photosphere. Though unimaginably dense compared to earthly standards, it is still a thin layer, only a few centimeters thick, where photons escape into space. This surface emits the light, X-rays, and other radiation we detect from neutron stars. Strong magnetic fields affect the surface profoundly. They guide charged particles, funneling them to the magnetic poles where hotspots glow brighter. It's a surface alive with energy, a boundary between quantum ocean below and the void above. The strongest material. Scientists believe the crust's lattice, reinforced by nuclear pasta, is the strongest material known, up to 10 billion times stronger than steel. This strength allows neutron stars to support mountains, tiny bumps only a few millimeters high but enormous by stellar standards. These bumps can cause gravitational waves as the spinning star wobbles slightly. Detecting such waves would open a new window into neutron star interiors. Thermal properties of the crust. Despite its strength, the crust is a dynamic thermal environment. Heat flows outward from the hot core through the crust, cooling the star over millions of years. The thermal conductivity is affected by impurities, magnetic fields, and nuclear pasta, creating complex temperature gradients. These variations can cause thermal hotspots and influence the star's emission patterns. How we study the crust. We cannot visit a neutron star's crust directly, but we study it through observations, timing pulsar glitches, measuring X-ray emissions, and detecting bursts from magnetars. Laboratory experiments on Earth simulate aspects of neutron-rich matter, but nothing matches the pressures and densities in a neutron star. Computer simulations help bridge the gap, modeling how nuclear matter behaves under these extreme conditions. Each discovery about the crust helps piece together the puzzle of what lies beneath. A frontier of extreme physics. The neutron star crust represents a frontier where nuclear physics, quantum mechanics, and astrophysics intersect. It challenges our understanding of matter and forces us to reconsider what solid means. From this crust emerge phenomena that ripple across galaxies: radiation bursts, gravitational waves, and precise pulses. The star's outer shell may be thin, but it holds the key to the star's life story. A surface to dream on. As you imagine this landscape tonight, the strange, dense crust beneath an ancient star, you are contemplating one of nature's greatest extremes. A place where matter is compressed, contorted, and arranged beyond earthly experience. A surface that glows faintly, shines in X-rays, and pulses rhythms across the cosmos. A fragile shell holding an eternal quantum ocean within. Among neutron stars, some shine with a unique brilliance: pulsars. These spinning remnants emit beams of radiation, sweeping through space like celestial lighthouses. Tonight, we'll explore how pulsars turn their rotation and magnetic fields into cosmic signals that travel across the universe. The birth of a pulsar. When a massive star collapses, its core becomes a neutron star. If the star's magnetic axis is tilted relative to its spin axis, it becomes a pulsar, a beacon rotating with astounding precision. These stars spin incredibly fast, some making hundreds of rotations per second, sending beams of radio waves, X-rays, or gamma rays out into space. From Earth, we detect these pulses as regular flashes, like the ticking of a cosmic clock. How pulsars work. Pulsars emit radiation from their magnetic poles. Because the magnetic axis is misaligned with the rotation axis, the beams sweep in circles. When one of these beams crosses Earth, we see a pulse. This lighthouse effect makes pulsars some of the most precise natural clocks known. The rotation slows over time as the star loses energy, but some pulsars remain astonishingly steady for millions of years. Types of pulsars. There are several types, including radio pulsars, detected by their radio emissions. These were the first discovered and remain the most studied. X-ray pulsars, often found in binary systems where the neutron star accretes matter, producing powerful X-rays. Millisecond pulsars, old neutron stars spun up by accretion, rotating hundreds of times per second. Each type tells a different story about the neutron star's history and environment. Pulsar timing and discoveries. Because pulsars are so precise, scientists use their pulses to test fundamental physics, general relativity, gravitational waves, and the interstellar medium. Pulsar timing arrays even search for gravitational waves from supermassive black hole mergers. In 1974, the discovery of the first binary pulsar provided indirect evidence for gravitational waves, confirming Einstein's predictions. The pulsar wind. Pulsars emit a wind of charged particles that interact with surrounding space, forming glowing nebulae. The famous Crab Nebula is powered by a pulsar at its center, its wind creating spectacular light shows. These pulsar winds shape their environments and inject energy into the galaxy. Pulsars as cosmic tools. Because of their precision, pulsars help astronomers map the galaxy, measure distances, and explore space-time. They may one day assist spacecraft navigation or even become part of a galactic GPS. In recent years, a new way of hearing the universe has opened, a way not through light or sound, but through ripples in space-time itself. These are gravitational waves, and neutron stars play a starring role in this cosmic symphony. Tonight, we listen closely to how neutron stars create, shape, and reveal these whispers from the fabric of reality. What are gravitational waves? Predicted by Einstein over a century ago, gravitational waves are distortions in space-time caused by accelerating masses, like two neutron stars orbiting each other. These waves travel at the speed of light, stretching and squeezing space as they pass, carrying information about the most violent events in the cosmos. Neutron star mergers, a source of waves. When two neutron stars spiral together and collide, they produce powerful bursts of gravitational waves. Detectors like LIGO and Virgo have captured these waves, confirming their existence and opening a new window into the universe. The waves tell us about the masses, spins, and even the internal structure of neutron stars, revealing what lies inside them. Continuous waves from spinning neutron stars. Besides collisions, spinning neutron stars with tiny mountains on their crust can emit continuous gravitational waves. Though weaker than merger signals, these waves offer another way to probe neutron star interiors and test physics under extreme conditions. The future of gravitational wave astronomy. As detectors improve, we'll hear more from neutron stars, more mergers, more continuous signals, and perhaps new, unexpected sources. Gravitational waves complement light, neutrinos, and cosmic rays, giving us a fuller picture of the universe. A new age of listening. With gravitational waves, we're not just seeing the universe, we're feeling it. And neutron stars, those dense, spinning remnants of stellar death, are among the loudest voices in this new cosmic chorus. As our journey comes to a close, we linger on the profound mysteries and quiet majesty of neutron stars. The collapsed hearts of massive stars, spinning silently in the vastness of space. These stars are paradoxes, small but massive, silent but powerful, simple in composition yet complex in behavior. They challenge our understanding, pushing physics to its limits. Cosmic remnants and seeds of creation. Neutron stars remind us that endings are also beginnings. Their collisions forge the elements that build planets, life, and even the devices you hold in your hands. They are storytellers of cosmic evolution, keepers of secrets written in dense matter and quantum waves. The beauty of extremes. From their superfluid cores to magnetic storms, from nuclear pasta to gravitational ripples, neutron stars embody extremes beyond human experience. Yet they connect to us, through the atoms in our bodies, through the gold on our fingers, through the very fabric of space-time. A universe alive with wonder. As you rest tonight, remember that the universe is full of marvels, hidden places where matter behaves like poetry, where gravity sculpts time, where light dances to cosmic rhythms. Neutron stars are one chapter in that grand story, silent, steadfast, and endlessly fascinating. Your place among the stars. You too are part of this cosmic dance. Born from stardust, bound by gravity, shaped by forces both fierce and gentle.